The notes for Unit 8, Lesson 3 will cover strong and weak acids and strong and weak bases. So after the notes, you'll be able to state the difference between the two and understand a little more how the pH relates to concentration. So make sure you have your notes packet. And here we go. So the definition of a strong acid is an acid that completely dissociates in water. So remember, dissociates, means to break apart. So basically, strong acids will have every single molecule break apart. So if you have HCl in this beaker, here you have your HCl molecules. So say we have 3 HCl molecules. When you put the hydrochloric acid in water, you will have all 3, you'll have all 3 molecules that break apart into ions. So every single molecule is going to break apart in solution. And those ions will be floating around. So you have 100% dissociation with strong acids. So if every single molecule breaks apart, then there's going to be more H+ ions floating around in solution, which means it's a stronger acid, which means it's going to have a lower pH, because on the pH scale, acids are 1 to 7. And so the closer that the solution is to a pH of 1 is going to be a stronger acid. Weak acids will only partially dissociate. So some of the molecules will break apart, but some of them will stay together. So weak acids will partially dissociate in water. So if you have a beaker, this is actually acetic acid, which is vinegar. So when you have a solution of vinegar, I'm going to actually draw the 2 ions. So these would be your 2 ions. Say again, we have, well, we'll make 4 molecules for this one. So when vinegar is in solution, what you'll see is some of the molecules will break apart, but some of them will not. So some of them will stay together. And because they only partially ionize, you're going to have fewer H+ ions in solution, which means that your pH will be closer to the neutral value of 7. So weaker acids will only partially dissociate or break apart, but strong acids, every single molecule is going to break apart in solution. And then bases, of course, are going to be the same, but instead of breaking up into H+, it'll form an OH-. So again, strong bases will completely dissociate, which means every single molecule will break apart. And weak bases will only partially dissociate or break apart. So one other thing that I want to point out with the difference between these two, since strong bases have solutions that will completely dissociate, you'll see a single arrow just going to the right, meaning every single molecule is going to break up into these 2 ions. We won't have any of the actual NaOH compound left when it's in solution. Whereas if you have a weak base or a weak acid, you'll notice this double arrow, because some of the molecules are going to break apart to form Rb+ and OH-, but some of them are going to stay together as RbOH. So that's another way that you can recognize strong and weak, is by looking at the arrow. So this picture is a little blurry, but you can see the pH scale starting with 0 and going to 14, and then it has some examples off to the right of what each of those pH values would represent. And then over on the left is the concentration of hydrogen ions. So here's what I wanted to point out. If you have like something with a pH of 5, whoops, I'm gonna fix my circle over here. So if you have a substance with a pH of 5, like coffee or soft drinking water, so that would be like tap water, and you're comparing it to something with a pH of 3, which would be like orange juice or soda, the substance with a pH of 3 is going to be 100 times more acidic than the substance with a pH of 5. So when you look at this chart, whoops, every step up you go in pH is 10 times greater. So between a pH of 7 to 6, the urine or saliva is 10 times more acidic than pure water. And then if you go another step up between urine and saliva and drinking water, that's another 10 times more acidic. So each pH value that you change is 10 times more acidic or 10 times more basic. So if we went from a pH of 8 to a pH of 11, this would be 10 times greater, this would be 100 times greater, this would be 1,000 times greater. So each bump in pH represents 10 times more acidic or 10 times more basic. In this case, seawater would be 1,000 times, or sorry, I said that wrong. Ammonia solution, which would be like similar to Windex, has ammonia in it. So ammonia would be 1,000 times more basic than seawater because you have a pH of 8 compared to a pH of 11. So I just wanted to explain that as well because it's not just a small difference. It ends up like every step is 10 times more acidic or 10 times more basic. And then last but not least, here is a list of 6 strong acids and 6 strong bases. Some of these you'll have heard of, probably more so the acids. Nitric acid, sulfuric acid, hydrochloric acid, those are probably the 3 more common ones that you've heard of. And then here is sodium hydroxide that you may have heard of as well. So those are just some examples of strong acids and strong bases. In your notebook, you will look up to see what some of the uses for the strong acids and some strong bases are and how they're used in industry. So as always, let me know what questions you have.